Science and Marine Science double major at Eckerd College. Let me send you, there we go.
Right. Double check, you can see this?
Yes, we see your whole, like, just the picture.
Desktop. Yeah, that's fine. All right. Sweet. All right, hi everyone. My name is Mark Yamane. I'm an incoming senior at Eckerd College. I'm majoring in marine science and computer science. And this summer, through the Holling Scholarship Program, I had the opportunity to work with Dr. Qidong Zhang at the Pacific Marine Environmental Lab for work on validation of ECMWF ensemble forecasts against saildrone observations in the Arctic. And so for a little bit of background, accurate weather forecasting of the Arctic is pertinent for management and conservation of marine resources and coastal communities. And especially as sea ice is diminishing at unprecedented rates, this is becoming more and more important. And predicting conditions in the Arctic is difficult because of a lack of in situ observations. As Lily said prior, without observations, well, the Arctic is just difficult because of things like sea ice. It's hard for people to go out and collect data. And so without these in situ observations, it's hard to develop the physics for the Arctic in forecast models. But saildrones allow us to sample the Arctic. And so the main objective of this study is to confirm results from Zhang et al. 2021, which used deterministic forecasts from multiple forecast centers against Arctic saildrone data. In this study, we use ensemble forecasts from a single center, and we want to see if the results are similar. In the process, we'll also do some general model validation as well. So saildrones are unmanned surface vehicles. They're remotely piloted, and they have a camera with machine learning so that they can actually navigate through these difficult conditions. So for the Arctic, things like sea ice, they want to navigate around. And you're able to attach all these sensors to measure a variety of environmental conditions, as listed on the right side figure here. The variables that I looked at were wind speed and wind direction through the zonal and meridional wind velocities, and air temperature, humidity, air pressure, and skin temperature, or sea surface temperature. And like I said, because it's remotely piloted, because it has all these sensors, this allows us to collect real-time in situ data in the Arctic. And so in 2019, NOAA led an Arctic mission that involved 4 saildrones deployed from May 15th to September 30th, 2019. And they sailed through the Bering, Chukchi, and Beaufort Seas, as you can see on the right side here. This is the trajectories of those during that mission. And just to show you what the conditions look like, why it's hard for normal observation sampling, the saildrones had to sail through and navigate through sea ice like this. This is from one of the cameras of the saildrone. So now I'll talk about the different types of forecasts that we used. So deterministic forecasts are forecasts where the entire projection is determined by the initial conditions. So on this figure here, let me get my laser pointer. If we wanted to focus on this little circle with an X, let's say that we set certain parameters a certain way for this X. Then we want to follow it. The deterministic forecast will just let the model run and just see where it ends up after we get to the final projection. So as we get to some sort of forecast time in the future, we want to see where that variable ends up. Well, for ensemble forecasts, you do multiple runs of this deterministic forecast, except you perturb the initial conditions. So you change the bunch of the different parameters a little bit in different directions, and we want to see where those end up going at the same point. And so this allows us to show the range of the model uncertainty over time. And what we typically see for ensemble forecasts is that error is initially small because you only change the initial conditions a little bit, but then it grows with lead time in different directions. And so you can see the spread here. Each of these lines, they're called ensemble members for each of the forecasts. The ensemble members start to spread out. And so this is typically, this is due to the butterfly effect. You just change small changes at the beginning. As you bring it over time, they could change a lot. And so we used ECMWF ensemble forecasts. So ECMWF stands for the European Center for Medium Range Weather Forecasts. It's an EU forecast center in Reading, UK. We use global ensemble forecasts, so the grid points span the entire globe with a grid spacing of 0.5 degrees in latitude and longitude. They have 137 vertical levels and 0 to 15-day forecasts for each of the initialization periods, and 50 members, so 50 of the ensemble member lines that you saw in the previous chart. We use surface forecasts, so not all 137 vertical levels. We use surface forecasts initialized every day at 00Z, or the beginning of the day, from June 2019 through August 2019. And then model output was linearly interpolated to the 4 saildrone locations to bring it from those full grid to just the saildrone points, get the same value at the same saildrone point for that time. So once the output was interpolated to the saildrone data, we're able to start pairing the observation with the prediction. So the blue lines for these figures are the forecast, prediction, and then the orange line is that saildrone observation. The left side is surface pressure, and the right side is sea surface temperature. And you can see here at the beginning, the top graph is at initialization, so predicting for the same day. And then as you go down these graphs, these are from predictions further out in time. So at initialization, you can see that sea surface pressure or surface pressure is good at the forecast is able to predict surface pressure really well at initialization. And then at 5-day lead, which means that this is the same time point from 5 days prior, it's a prediction. You can see that there's begins error. It's not as good as at initialization. And then at a 10-day lead time, so from 10 days prior, this prediction at the same time points, you can see that error starts to grow, and it grows at 15-day lead. It's pretty much reaches its saturation point, meaning this is all model systematic bias. It's not really any skill in the forecast at that point. And then for sea surface temperature, we can see that it begins with a little bit of error. So whereas in surface pressure, it matched the observations pretty well. At sea surface temperature, it begins with a little bit of error, and it grows over time, but you can still see patterns even out at 15-day lead time. The change in the error doesn't change as much as you predict further out. And so these results are actually similar to the Zhang et al. Paper, where dynamical variables began with little error and then grew over time, and thermodynamic variables like sea surface temperature, air temperature began with some error, but they stayed pretty consistent over time as you try to predict further out. And so now we're going to look at the different characteristics of this is called the spaghetti plot. So for each of the saildrones, I plotted the ensemble members and the observation. Saildrone observation is the orange line for the saildrone. And on the x-axis is lead time. So from initialization to 15 days out, this is what the observations are, and this is what the predictions. The thin gray lines are each of the ensemble members' predictions. The blue line is the ensemble mean, so it's the mean across all of the ensemble members. And so here we can see that, again, at the beginning, everything's very close together, the members and the observations. And so that tells us that the error is pretty small at the beginning. But then it starts to spread out. This is what I meant by the spread. The ensemble members go out in different directions over time, just showing the range of uncertainty of the model. And so if we wanted to calculate the error, that's just the ensemble members minus the observation. And so the graph for that would just look like the observation flattened down to y equals 0, and then we can look at the error from there. And so the error for these graphs look like this, where again, you see around 0 error at the beginning, but then it increases a little bit over time. Once we have error for each of the saildrones, we're able to combine those by taking the mean across saildrones. And so this is actually what I did for all the statistics we see in the following slides. This is just to show you the process of what that looked like. So the first ensemble statistic we want to look at is spread skill relationship. So spread skill relationship looks at root mean squared error, or RMSE, and S, which is the spread. And so ensemble forecasts are meant to represent the full uncertainty range of a model. And so when we look at spread skill relationship, we want to see how close the error is to the spread. When the spread is too far below, that means that the model is under-dispersive, meaning the spread is really small, and it might not actually capture the true value. And if it's far above the root mean squared error, then it's over-dispersive, meaning it's underconfident, and it might capture the true value, but the spread is way too wide. It's not realistic in terms of variability. So we want to see these two lines close together. The perfect ensemble would have the mean of the spread equal to the RMSE over the same period. And so we see that there's a good spread skill relationship for surface pressure and the wind components. Whereas for the thermodynamic variables like air temperature, sea surface temperature, and relative humidity, the spread is pretty under-dispersive. It's pretty confident. So this shows that the forecast is pretty reliable for the dynamical variables. We also looked at signal to noise ratio. So you can think of the signal as the ensemble mean and the spread about the mean as the noise. And in general, you can think of a higher SNR as being more reliable, a more reliable forecast. And y equals 1 would mean the signal equals the noise. So at that point, we lose reliability. That's really what we're looking for when the signal to noise ratio is below or reaches y equals 1. And so at the beginning of the signals, of the lead times, remember at initialization, the signal is really strong. And so that's why the graphs are so large at the beginning. So let's zoom in a bit so we can actually see the y equals 0 line. And so now that we can see the y equals 1 when signal equals noise, we can see that it's pretty much, the forecast is pretty reliable for all of the variables up until a week, for everything except for, for everything up to a week. And then sea surface temperature actually stays above y equals 1 throughout the lead times. And this was kind of an interesting finding, but it makes sense when you think about the time series of the sea surface temperature. That variability didn't really change, and the model was actually able to predict pretty well at the 15-day lead time. So the signal was still pretty strong at day 15. And so in conclusion, these results were consistent with Zhang et al. 2021. Error began small for the dynamic variables, but increased with lead time. And then it became large for thermodynamic variables, but stayed consistent over lead time. Our spread skill relationship indicated a skillful spread for pressure and wind, but not for temperature or humidity. And our signal to noise ratio indicated a reliable forecast to a week for all of the variables except relative humidity. And so for the next steps for this project would lead to the computation of a rank histogram, which is developing a probability distribution of observation value ranked among the ensemble members. And then for just more ensemble statistics, if we wanted to validate for longer forecast skills, what I did was on instantaneous interpolation. So we interpolated for the exact day, the exact time, exact location. And you can actually get the signal to noise ratio to extend further than 15 days, probably way further than 15 days, if you try to predict the averages over days or weeks or months. I tried to do the instantaneous value, which is why it only went out to like around a week. And in general, more saildrone deployments will allow this study to be expanded to other regions. So that could be exciting to look at. So I would like to thank Qidong for his guidance throughout the project, the PMEL Air Sea interns for support over the summer, PMEL for hosting meaningful virtual events for this virtual internship, saildrone for operating the field deployment, ECMWF for access to the forecast data. And from Eckerd College, I would like to thank Dr. Mike Hilton and Dr. Kat Robinson for helping me apply for this scholarship. And this project was funded again by the NOAA Ernest F. Hollings Undergraduate Scholarship Program. That concludes my presentation. I'm happy to take any questions.
Good job, Mark. With that, the floor is open for questions.
Yeah, I have one. Great presentation. I was curious about with the SST, signal to noise ratio. Were there any thoughts on why that was kind of bouncing up and down?
That could be due to some sort of diurnal variability. That's a good question, by the way. That could be due to the diurnal variability that Lily kind of talked about. We do kind of see some peaks in some of the other. We can go back to that slide. So for other thermodynamic variables, I guess not air temperature, but we can sort of see this pattern as well. So we could think of that as diurnal variability. We had points at every 4 hours. But that could be something to look into again, and maybe might be interesting to see along with Lily's findings for diameter cycles.
Thank you.
Other questions?
Nice job, Mark.
Okay, well, I guess if no other questions, we are gonna take a break. I do think we had some time zone changes, and I think actually our next presenter